The train, a symbol of progress and sustainability, is at a decisive moment. The GSM-R radio system, the backbone of high-speed railway communications for decades, is reaching the end of its life cycle. The International Union of Railways proposes its replacement, FRMCS, a new interoperable standard based on 5G and MCX, set to revolutionize train-to-ground communications. In this context, Moisest was born, a project aimed at accelerating the digital transform of rail transport. Moisest is an initiative led by Teltronic and funded by the UNICO Sectorial 5G program, supported by the Ministry of Economic Affairs and Digital Transformation through the Next Generation EU funds. The goal? To develop and integrate a critical train-to-ground communication solution over 5G radio networks and MCX technology, aligned with the new FRMCS standard.
While the initial launch phase of a new standard such as FRMCS focuses mainly on defining functional requirements and translating them into specifications and interoperability forums, the Moisest project has allowed us to take a broader and more integrated view from the very beginning. We have considered the full set of elements involved in a real-world solution, which has enabled us to anticipate the challenges of a technology as complex as railway communications, minimize the inherent risks in deploying new standards, and prepare ourselves to deliver to the market efficient solutions fully aligned with the needs of such a demanding environment.
For months, technical teams worked in the lab to design a secure and functional solution. Development followed the guidelines set by ETSI and 3GPP, in line with Teltronic's commitment to promoting international standards. This approach enabled the design of a robust 5G infrastructure and the consolidation of an interoperable MCX solution, ready for demanding railway environments.
The project introduced complex engineering challenge for Teltronic R&D department, driven by the stringent requirements of high-speed railway environment. The team deployed a 5G private network fully aligned with FRMCS standards to guarantee ultra-reliable, low latency communication for mission-critical services such as signaling, real-time video, and voice over IP. These require advanced radio planning to mitigate Doppler effect at the speeds above 200 km per hour, seamless inter-cell handover, and dynamic QoS slicing to prioritize safety-critical traffic. A key component was the integration of Novax, which is the Teltronic MCX solution, both in the onboard equipment and the control center, enabling secure mission-critical voice and multimedia service over IP. Additionally, the architecture incorporates robust cybersecurity layers like Toolbox, NESAS, and SCAS.
Durango, in the Basque Country, was the stage for the first real-world operational tests. Over several nights, outside commercial hours, a Euskotren commuter train equipped with 5G radio and MCX technology ran along a specially prepared section in collaboration with ETS. On board, engineers monitored every detail, while from the control center, voice, data, and video communications were verified in real time. It was an intense effort. Installing the private 5G infrastructure meant overcoming major challenges, such as ensuring coverage in tunnel sections, where Teltronic's project management experience proved essential. The outcome was the best possible. Metrics confirmed system viability. Coverage, latency, stability, and security met the performance standards expected under FRMCS. With all the experience gained in the Moisest project, the Teltronic team faced an even greater challenge: to validate an end-to-end FRMCS solution that was 100% developed in-house in a high-speed environment. To do this, it deployed a private 5G network covering a total of 37 kilometers of the Madrid-Alicante line.
There are obviously challenges intrinsic of the technology, in this case 5G. We also have challenges of the frequency that we were allowed to use. It's a high frequency, 2.4 gigahertz. And then we had the challenge of the market. We were targeting the project to a railway scenario, and in a railway scenario you have to comply with certain availability and reliability very high. If we go to the different phases of a project, I could say that in the design phase, that's where we focus most of our challenges, trying to build and design a system that would comply with the coverage requirements and the data throughput that was requested to do the test. That imply, and the environment itself. We were testing in an environment where we were going from open track into a tunnel and out of the tunnel. Also, in some section of the tracks, we were going more than 200 kilometers per hour. That was another challenge. Then we go to the other phase I mentioned, the manufacturing integration of the equipment. That phase, basically, the challenge was to how can we configure the equipment that can comply with those requirements? How can we emulate those scenarios? We did that in the lab. We used certain equipment to try to simulate the best that we could. Then we had the installation typical challenges. I have to say here that mainly the fact that we were working in a commercial railway track implied that we could not spend as much time as we wish. We had only small windows to do all the installation, and including we had small windows to do the testing.
For this new challenge, carried out with the collaboration of ADIF, state-of-the-art onboard equipment equipped with an MCX client was installed on a train. From there, at speeds of up to 200 kilometers per hour, voice, video, and data communications were sent, including geolocation and a constant flow equivalent to that of railway signaling. The 5G core, MCX server, and control and dispatch center were installed at the Bonite Technical Center. Inside, Teltronic engineers tracked the train in real time, ensuring all communication services remained fully operational. After days of testing, with the train covering more than 900 kilometers, the results were conclusive. Quality of service and transmission rates reached the levels required to guarantee FRMCS services for voice, geolocation, railway signaling, and even real-time video streaming. Calls were made from onboard radios, mobile terminals with MCX apps, and the dispatch center. An interoperability exercise was also conducted, successfully validating MCX roaming between 5G systems across borders. Cybersecurity, one of the project's key aspects, was also tested, with every induced anomaly detected, logged, and mitigated.
After 3 years of cross-functional cooperation among multidisciplinary teams, we have designed, integrated, and validated both in the lab and in the field, a fully representative FRMCS solution architecture. This solution brings together 3 key elements: MCX technology, an optimized 5G network, and a robust cybersecurity layer. We deploy onboard equipment, radio infrastructure, and dispatch systems. Its performance and interoperability have been tested in 2 privileged real-world environments, one metropolitan and one high-speed. This is beyond doubt a major breakthrough, strengthening our commitment to driving FRMCS forward and position ourselves for the imminent arrival to the market.
Teltronic positions itself as a benchmark in railway innovation, with a solution fully developed and deployed by the company, demonstrating for the first time the complete operation of an FRMCS solution. A replicable, interoperable model ready to transform railway operations, with which Teltronic sets the course toward the transport of the future.